What up, everybody? We just finished lab, and now I'm going to teach you how to analyze gels. Okay, so in class we went over what a gel is, what it looks like. You probably practiced a little bit, so I'm going to do that part quickly. Anytime you run a gel, you're going to run a ladder. A ladder is a set of known pieces of DNA and some dyes. The ladder that we're using is called the NEB tri-dye 2-log ladder. You can screenshot this, and you will need this information because you will need to look it up here. Okay, so there is both DNA and dye that is together in my ladder. When I run my gel, I'm going to run 2 microliters of this ladder along with my sample. When I'm looking at it, I'm going to look at the dyes. When I'm looking at it, when I say looking at it, I mean with my eyes, I'm going to look at the dyes. This orange dye travels with 50 base pairs. This dark blue dye travels with 300 base pairs of DNA. And this light blue dye travels with around 4 kb. Hey, Paul. No, I'm just explaining how to look at gels. All right. Forgive the intrusion. All right, so 50 base pairs, 300 base pairs, and 4,000 base pairs. This is going to be super important because what I can do, 2 things, is I can run my gel for too long and I can run my DNA off of it, or I can run it into another set of DNA. So let's take a look at this gel again. This is where I load my DNA. And this is the DNA after it has traveled. So you have small pieces of DNA here, you have larger pieces here. If I ran this DNA for too long, then it would have traveled into this second set, and we would have overlapping pieces of DNA, and it would be a problem. Now, what we're looking at here is actually the gel that has been put in a dark chamber and then shined UV light on it. The UV light is picking up DNA dye, so everything that is bright here is DNA. On the left here, we have the ladder. Again, our tri-dye 2-log NEB ladder, and that will give us the sizes of the DNA. So if I go back to my data sheet, I can see this is what my DNA dye, or my ladder looks like when it's lit up in what we call the gel box. So here we have 0.1 kilobases, which is 100 base pairs, 200 base pairs, 300 base pairs, 400 base pairs, 500 base pairs, 600. And here it looks all fine and good. And then you come over to this, and you're like, this does not look like this. So you're like, what the heck do I do? Well, you'll notice that there's some bright bands in here, and there are some dark bands in here. For example, this is bright, this is bright, this is bright, and this is bright. And that's going to be really, really important for us because we see that same pattern throughout all the ladders, and that's going to give us a clue as to what size everything is. Again, we're going to run 2 microliters of our ladder when we do this. So here I have a bright band, and a bright band. So this bright band is going to be 500 base pairs, this bright band is going to be 1,000, and then this one up here is going to be around 3,000. And I know that because I look here, 500, 1,000, 3,000. Okay, so 100, 200, 300, 400, 500 base pairs, and then 1,000 base pairs. And if you look in there, you can see that there's a division in there. So right around there is 800 base pairs. This is where my DNA showed up. If my DNA was supposed to be 800 base pairs from one end of the primer to the other, again, the distance between the primers plus the beginning of the primer. So we're not just doing the distance between, but from the beginning of one primer to the end of the other. Here should be 800 base pairs. Now let's talk about some things that I did wrong with this gel. Here you can see the primers are really bright. They shouldn't be this bright. As a matter of fact, you should barely see them. It should look more like this, which means I need to cut my primer concentration, and I would probably cut it by a factor of 10. Here, my gel didn't run long enough. My ladder rungs are on top of each other. So I would have run this longer, or when I made the gel, I would have cut out this set of wells and just used this whole gel to run my DNA on. Okay. I also probably ran this gel too fast. You can see not only are the rungs overlapping, but they're kind of smudgy. So you see that smudginess here as well. That tells me that I've run my DNA too quickly. This jellyfishing, so this is not what a band should look like. A band should look more like this or like this, almost the same exact shape as the well. This means that I have a ton of DNA or I ran my gel too fast, which means my voltage was too high. That means I need to run it at a lower voltage. This gel was run at 120 volts, by the way. All right, so what's going on here? So in this reaction, I have primers, but I don't seem to have anything amplified. Okay, well, that can mean one of two things. My primers didn't work, or I didn't isolate my DNA. So how can I distinguish between those two things? Well, if I don't have any DNA, then it doesn't matter whose primers I use, I won't be able to amplify anything. So if I'm trying to figure out whether or not I have DNA, and I suspect that I do have DNA, if I use another group's primers that I know worked, then I should see a band here, and that means that I have DNA, but I need to check. Now, if my primers didn't work, that's going to be another problem. And the way we can figure out whether my primers worked or not versus whether or not I have DNA is by running my primers on several different people's DNA. So somebody had to have gotten DNA in one of the groups in this class. And if I run my primers with everybody else's DNA and it shows up, that means I have successfully isolated DNA. If I didn't successfully isolate DNA, I need to re-isolate DNA. If I didn't have successful primers, that's a little more complicated, and we'll need to talk about that. This was a crash course in looking at gels. I know everything I said didn't make sense, but I want you to watch it and see it anyway. It will always make more sense the second time you see it. I don't want Monday to be the first time you see any of this. I want it to be the second.